It's time to talk about bombs. The first atomic bomb I'm going to talk about was a so-called gun-type bomb nicknamed Little Boy, which was dropped on the Japanese city of Hiroshima and was a tremendous disaster for the people living there, killing at least 80,000 of them, perhaps as many as 100,000. The design of the Little Boy bomb was a gun. This was the bullet in that gun. It's a hollow cylinder, 6.5 inches in diameter, with a hole in it 4 inches in diameter, about 7 inches long. This was the target. It's a cylinder 4 inches in diameter, which fits neatly into the hole in the larger cylinder. Now, at rest, this would be fixed in the target area of the gun at the end of the muzzle, and this part would be way over here somewhere with the charge of smokeless gunpowder behind it. This gun, with a 6.5-inch bore, was manufactured by the U.S. Navy Gun Factory, which was then active in Washington, D.C. It was a naval-type gun, meaning the powder and the igniter for the powder were directly loaded into the breech of the gun. There was no cartridge containing all this stuff. When the gun went off, this part would accelerate rapidly, well, not too rapidly, about 1,000 feet per second into the target. They would come together, and there were some little initiators, 4 of them, on the inside of this plate, which would be squashed when the two came together, and which would emit neutrons in order to start the chain reaction. The secret of the success and the failure of this bomb has to do with neutrons. Here on Earth, we are constantly bombarded by neutrons coming from cosmic rays. The cosmic rays themselves are not neutrons. They're positively charged ions, but they run into atoms of our atmosphere and undergo various nuclear transformations, some of which produce neutrons. So we have a constant flux of neutrons on the Earth of between 1 neutron per minute and 1 neutron per second. And there's no predicting exactly when and where a particular level of neutron bombardment from cosmic rays will occur. So these 2 cylinders, which in total weight, if they were really uranium, I couldn't lift. They're 64 kilograms altogether, 140 pounds in this compact form, because uranium is a very dense metal. It's denser than lead. During the time that these cylinders are apart, if a neutron came into proximity with them, passed through, they might trigger just a little bit of fission, but they could not trigger a chain reaction, because each of these separately, in the shape it's in, does not constitute a critical mass of uranium. By the way, this isn't natural uranium. This is enriched uranium, at least 80% uranium-235, which is the isotope that is easiest to fission. Besides the neutrons that come from cosmic rays, there is also a small probability that the U-235 in these cylinders will undergo a different process called spontaneous fission. Spontaneous fission doesn't need a neutron to start it. It's a very improbable event, but it does occur, and when it occurs, like any other fission, it will release some neutrons. So basically, you have to be aware that a certain number of neutrons are going to be generated within this metal itself. A key concept in understanding these bombs is critical mass. And the thing that many people don't appreciate about critical mass is that it's not one number. A critical mass of uranium-235, for instance, can vary from, well, about 30 kilograms or so when there is no neutron reflector around, down to a considerably lower number, depending on whether it is in the form of a cylinder or a sphere or some other form. For instance, if you were to extrude uranium-235 as a wire, there is no length of wire which would constitute a critical mass, because it would lose so many neutrons out the surface of the wire that there would never be enough to sustain a chain reaction. However, if you wound that wire on a spool, very soon you would come to an unpleasant realization, which is that you've just killed yourself because you have started an ongoing chain reaction in the spool of wire as you're winding it. So it's very important. There's actually more than two critical masses in these two cylinders which were in the bomb. But because of their shape, this one is less than one critical mass. This one is more than one, but it's in a shape that permits a lot of neutrons to escape without causing another fission. When you bring them together, however, they will form a critical mass, probably about here. Now, the time period you have to be concerned about is from here to here, because during this period, you barely have one critical mass of uranium in this partly assembled bullet and target. And during this time, if a neutron starts a chain reaction, you will have a what's called a fizzle, an incomplete explosion of the bomb, because there's not quite enough fuel to give it the full strength, but there's enough to get a fission reaction started. What you want, what the designers wanted, is to have the thing completely assembled, so it's one solid cylinder like this, and then the little crushable neutron generators on the inside of this plate will release neutrons into the mass of uranium and start the fission process. Notice that the neutron generators are only on one end. You can expect the fission, if it gets this far, you can expect the fission process to start from this end and not to propagate all the way through, because it's always a race between the fission process in the metal and the explosion process of the metal heating up to a fantastic temperature and blowing apart as a gas of uranium. What happened at Hiroshima? It's certainly probably the greatest disaster that's ever befallen a modern city. How big was it, and how big was it intended to be? Well, consider this fact. There had been one nuclear test before Hiroshima, and that was the Trinity test in southwestern New Mexico. At the Trinity test, there was a different fissionable material. There was plutonium involved. And of the 6 kilograms of plutonium that was in that bomb, approximately 1 kilogram underwent fission. That's only about 15-16% of the total. You'd think that would be a disappointment. But it wasn't. 1 kilogram of fission translates to about 16 or 18,000 tons of TNT equivalent. This is the equivalent we have to be aware of. 1 kilogram is 2.2 pounds. 1 pound of these fissionable materials will yield approximately 8,000 tons of TNT equivalent in explosive power. So the 2 pounds that went fission at Trinity yielded this 16 to 18,000 tons of TNT equivalent. That's a really big explosion. By contrast, the explosion that occurred in the air above Hiroshima was maybe 15,000 tons of TNT, which translates to less than 2 pounds of uranium undergoing fission. Now, this big cylinder of uranium that I just showed you was about 64 kilograms or 140 pounds. That means that only 2 pounds out of 140 actually underwent fission. So, strictly speaking, this explosion of this bomb was a fizzle. A fizzle is an incomplete explosion of the fissionable material in an atomic bomb. And yet, it caused unspeakable disaster to the people underneath it. If the yield of this uranium bomb had been closer to the yield of the plutonium bomb that was tested a couple weeks earlier, then it would have been more like 50,000 tons of TNT. It would have been a really big explosion, and it would have done even more damage and killed even more people and spread even more fallout. We can be grateful that it was a fizzle. It was not as bad as it could have been, but it was still pretty bad for those people underneath it. So that's the story of the first bomb. Next time we'll talk about the second one.